Okay, let's start. Sorry for those of you on YouTube. I got a great, while we were at Playland yesterday, in fact, on my YouTube feed, I just got a comment from someone I've never heard of, and it was, OMG, why did you yell? And I was like, yeah, welcome up. Someone must have been listening with headphones and watching my YouTube videos. What we want to talk about today is terminology. We're going to break circuits up into two main types, series and parallel. You may have heard this if you've done anything techie. Oh, those are wired in parallel. Those are wired in series. A series circuit is a circuit where all the resistors are connected in a row with no junctions in between them. In my ski hill analogy, it's hills that all of the skiers have to go down because there's no forks in the trail. Which circuit of these two shows resistors in simple series? That one. Here, there's a junction. That is not a series circuit because now current splits up and has the option of going one way or the other if they're skiers. Okay. Example 2 says, find an expression for the total resistance of a series circuit. There is a lovely derivation, but in the interests of time and because you guys also have your Playland assignments, I'm just going to give you the answer. If you notice that a circuit like the one there with R1, R2, and R3 is in series, if you want the total resistance, it's just going to be R1 plus R2 plus R3. That is not on your formula sheet. You'll have to memorize that. That if you want to find the total resistance of something in series, you add them up. Well, that's not that tough to memorize, but okay. Why do we need that? What we're going to start to look at are circuits that are so difficult that we can't solve them as is. What we need to do is rewrite them as their simplest mathematical equivalent, solve the simplest mathematical equivalent, and then morph everything over into the more complicated circuit. So, if we're in series, our total is going to be R1 plus R2 plus R3 plus R4 plus R5 plus, that's why I have dot, dot, dot. Okay. And this already, I started out with that battery light bulb problem before class started. This already is going to give us a better way to handle it. So example 3 says, select the best answer for the voltage drop across the 20 ohm resistor. We're actually going to go further than that. We're going to solve this. We're going to solve this. I'm going to find out the voltage drop, the current going through each resistor. Did they tell me current anywhere? And I told you, Dustin, that I want to try and find total current. Do you see amps anywhere? No. This is a situation where we're going to have to rewrite this circuit as its mathematically simplest equivalent. These two resistors are in series. There's no junctions between them. You agree with me? That means I can replace this with one 25 ohm resistor. I can add them together. The mathematically identical circuit, and we're going to draw this to the right, is this. Battery, one single resistor, where the battery is still 100 volts, but mathematically, a 5 followed by a 20 ohm resistor is the same as a single 25 ohm resistor. Now, why is that so handy? Because V equals I times R. What did we call that? Behind the letter O? It's Ohm's law. Give me 1 second. Pause the video. We called that Ohm's law, but I'm going to expand it. Not only is V equals I times R, anywhere in the circuit, total voltage is total current times total resistance. Look at that blue circuit that I've drawn. What's the total voltage? 100. What's the total resistance? Okay, can you get the I by itself in here? I equals V over R. Remember I said if you can find total current, your question falls apart. I'm telling you, Raj, we can find total current. It's going to be 100 divided by 25. In your head, Dustin. Nice. For what? Current. Okay. That's the mathematical equivalent, but here's what that means. Flowing from the battery, skiing from the chairlift. How many amps? Flowing from the battery, skiing from the chairlift. How many amps? How many amps? How many amps? How many amps? You know what? If I know two things, I know everything. How many volts? I times R. I lose 20 volts going through this resistor. How many volts am I starting with? How many volts do I have left if I've lost 20? So that should be 80 volts, but you know what? Let's prove it. Dustin, let's keep going. How many amps still? How many amps? How many amps? How many amps? How many amps? How many amps go through this resistor? Because there's no junctions. And if you go I times R, 4 times 20. You said mathematically using subtraction it should be 80, but we've also been able to use Ohm's law, and yeah, 80 volts. Exactly. That resistor uses 80 volts. The top resistor uses 20 volts. That uses 100 volts. This is a valid circuit. And so now I can actually answer this question exactly. It says select the best answer for the voltage drop across the 20 ohm resistor. 100 volts, more than 50, less than 50. You know what? Exactly 80. It says explain your answer. There. This is going to be our final strategy. I'm always going to try and find total current. I always see if they tell me that. If not, I always go look for anywhere they've told me two things, because that tells me four things and I can work some magic. If not, I'm going to rewrite the circuit as its mathematically simplest equivalent. I'm going to do a crappy sketch. I'm not going to worry about neatness or anything. I want to write it as, hey, one battery or voltage source and one resistor, and I can use V total equals I total, R total. There's a similar rule for parallel circuits, but it's a little more complicated. Oh, example 4. Here is a fair question. I would consider this a C+ level question. Right now it seems very daunting, but that's okay. So we would walk through this as follows. Kevin, I would look at this and I would say, what's the first thing I'm always trying to find? Do you see current anywhere? No. Then I would say, hey, maybe they told me two things on one of the resistors. No? No. I need to write this as its mathematically simplest equivalent. All three of these resistors have no junctions between them. That means they are in series. That means I can replace them with one resistor. How big? Add them up. In your head, what's 15 plus 5 plus 5? In fact, this is also mathematically the same circuit as the one above mathematically. When I go further on, the values will be different, but mathematically, this is a 100 volt source and a 25 ohm resistance, which means, what's the total current in this question? Yes. How many amps are leaving the battery? How many amps in here? How many amps in here? How many amps in here? How many volts do we lose going through the top one? Oh, please, it's 15 times 4 in your head. You tell time, you should be able to go, yes, 60. How many volts do I lose on the right-hand one? Leaving how many volts? Hopefully 20 volts left. Does that actually work? Yay, I've got a lovely confirmation that Kirchhoff's laws work within Ohm's law. Solving circuits. Skiing. Okay. Again, in our ski hill analogy, we would say 4 skiers, 4 amps, leave here. They all go down this first biggest hill, losing 60 volts. Whee! They all go down this smaller hill, losing 20 volts. In fact, these two hills happen to be the same height. They're identical hills. A parallel circuit, turn the page, is a circuit where the current splits up and then rejoins together. where resistors are starting and ending. I keep forgetting to change that. It's been 9 years now. Starting and ending at the same voltage, same height on the ski mountain. Says, which shows resistors in simple parallel. Looking here, the current splits up. Some go this way, some go this way, some go this way. But I notice they all meet up again right there. This is a simple parallel circuit. Now, the second one is not a simple parallel circuit. In the second one, these two are in series because between those two there's no junctions. If you wanted to, you could add them together and write them as one single resistor. And once you had done that, the mathematical equivalent of what I'd circled in red would be in parallel with this one here. This is what we call a mixed circuit. Find an expression for the total resistance. In the interests of time, I'm not going to walk through it. I'm just going to tell you we can't find total resistance. We can't find it directly. What we can find is its reciprocal. We can find 1 over total resistance. And it's equal to 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor. In fact, I'm going to stick some numbers here. I'm going to make this one a 2 ohm resistor. I'm going to make this one a 5 ohm resistor. I'm going to make this one an 8 ohm resistor. And I'd like all of you to get your calculators out because I want to show you a good trick. Okay? If I wanted to rewrite that as a single resistor, I would go like this. First of all, are they all in parallel with each other? Yep. Do we start and end at the same height? In other words, do we split up and all join back together? Then I can combine them as one. But indirectly, it's going to be 1 over the total resistance is going to be 1 over 2 plus 1 over 5 plus 1 over 8. Write that, and then I'll show you how we type that. I'm not going to get all complicated. This will work on any scientific or graphing calculator. 1 over 2, I'm going to type 1 divided by 2 plus. My divided makes a slash. Your divided makes a divided by. 1 over 5, I'm going to go 1 divided by 5 plus. 1 over 8, I'm going to go 1 divided by 8 equals. And then here's the beauty. I want the reciprocal of that. I want to flip it. All of you, if you look, you have a little x to the negative 1 button, which probably you've never bothered using. You have a reciprocal button. If you find that little x negative 1, that reciprocal button, you can just do that and take the reciprocal of the answer. This is a resistance of 1.212122121 ohms. R total equals 1.21 ohms. If you cannot find your reciprocal button, this is your chance to raise your hand and call me, and I will help you find it. So if we want to put this in the box, if you're in parallel, 1 over R total equals 1 over the first one plus 1 over the second one plus 1 over the third one plus 1 over the fourth one, and then take the reciprocal to actually get the R total by itself. Kiowa, that one also not on your formula sheet. So you will have to memorize series, add them together, parallel, add their reciprocals, and then reciprocal the answer. That's almost it in terms of I'm almost not going to be showing you another equation for the whole unit. The only other equation I'm going to be showing you is an extension of Ohm's law. You ready? I like example 7. I like example 7. Example 7 I would call C+, B- level question. There will be absolutely one of this level of difficulty on the test. What kind of a circuit is this? Parallel. Parallel. Okay. Clay, I want to solve this. Do you remember what I said I always look for first? Total current. No. Total current. Do you see amps anywhere?
No.
Okay. The second thing, and we're going to make a list, but I'm memory right now. Second thing I look for is anywhere where there's two things. Are there any resistors where they told me two pieces of information? Because if I know two, I can find everything else. No? I have to rewrite this as its mathematically simplest equivalent. I'm going to rewrite this as a 60-volt source and one single mystery resistor. This mystery resistor is the total resistance, R total RT. How will I find that? Over here, I'm going to go 1 over R total is going to be 1 over 10 plus 1 over 15 plus 1 over 20. Hit equals, and then flip that using your X to the -1 button. I'm deliberately not going to try this myself. Try this on your own. Oh, you got the X to negative? Yep, you're good. Yeah, you should. Even a cheap scientific calculator almost always has that reciprocal button. Really handy for this. I think this might work out nice. Oh, no, I stand corrected. Do you get 4.615? That? I'm going to write on my picture 4.6. But I'll use my answer button in my calculations. Do you get that okay, Vikas? You typed it wrong. You went 1 divided by 10 plus 1 divided by 15 plus 1 divided by 20 equals reciprocal? You typed it wrong. It has to be. Yeah.
My calculator, I do it, and then it puts it in, when I hit equals, it's already in fraction form.
Excellent. So we can fix that too. Give me 1 second. I don't want the resistors as fractions. I want them as decimals. So anyways, I mean, fraction is nice because that's not rounded off at all. And so if I was doing math, I'd certainly prefer that. I'm just going to write 4.6. Here is the key now. I'm interested in what's the total current. It's going to be 60 divided, it's going to be V total over R total. It's going to be 60 divided by, I'm going to write 4.6, but I'm going to use my answer button. Oh, it's probably going to be 13, because the fraction happens to be 60 over 13. That's a lovely coincidence. So 60 divided by answer button, yeah, 13 amps. Okay? How many amps are leaving right here? 13 amps, right, Clay? I think you were the one I was picking on. How many amps right here?
13.
How many amps right here?
15.
Here, splits up, and I don't know how yet. Okay, but it did say find R total, check. It did say find I total, check. Do I know how it's split up? Say no. Let's ski. This is my final strategy. How high is this chairlift?
13.
How high is this chairlift? How many volts is this?
60.
So we have 60 volts to play with, okay? That means if I do a full loop, I have to use up all 60 volts. Here is one possible ski run. Did that get me back to the bottom of the chairlift? How many volts must I lose going through that 10 ohm resistor? Do I know two things? I know three things. How many amps are there going through this resistor? I'll give you a hint. V over R, V over R. 6 divided by 10. You said it? Yeah, I said it again. I was talking.
6.
Nice and loud so the...
What number am I saying now?
How many amps are going through here?
6.
Yeah, sorry, I wanted you to say it loud so my mic picked it up because I was talking while you were going. Say it loud and proud.
6.
Thank you. Hey, Clay, here's another ski run. Here's another ski run. How many volts must I lose going through the 15 ohm resistor? 60. This is why I said last day, this bugs a lot of kids because now they're like, well, that's 120 volts. Voltage doesn't add up. Current adds up. Voltage does not. So 60 volts. How many amps must be going through that resistor?
4.
How many volts must I lose going through the 20 ohm? That's another path that gets me to the bottom. Loud and proud.
3.
And if you add up, oh, I did it in black. Let me be consistent. If you add up all of the numbers that I've written in black, please tell me you get 13 amps, do you? There you go. So we have 2 ways we could get total current. We've got confirmation along the way. Okay. For this one, I probably, rather than rewrite this, I would have skied first, knowing that I could find each current and add them up. But what if they didn't give me one of the resistors? They could have done that. They could have left a resistor blank. And I could still find everything by a process of elimination still. Example 8 says, what can be said about the voltage drops across the resistors in the circuit below? You know what? Let's just find the voltage drops in every single resistor there. This is a very tricky one. This is one of the few times when I'm going to have to use some of those shortcuts I talked about last class that I said I don't normally memorize. And I'll show you what I mean. Spence, you ready? I always want to try and find total current first. Did they tell me total current?
Yes.
Okay, this question's going to fall apart. I always have that confidence. How many amps are there going through this circuit?
5.
Right here, 5. Do I know how they split up here?
No.
Yeah, come back to it. Do I know how they split up here? Come back to it. Do I know how they split up here? Are those identical resistors? Then how would they split up the current if they're identical resistors? This is the only time I use that shortcut. 2.5 amps, 2.5 amps. Okay? Then, if I was really clever, I could probably use that ratio trick. I'm not clever. I'm going to rewrite this as its mathematically simplest equivalent. See, the reason this one is so tough is I don't even know the battery. Did they tell me the voltage of the... Okay, I got to find everything. These 2 circuits, these 2 resistors here are in parallel with each other. These 2 resistors here are in parallel with each other. In other words, I can redraw this circuit and I can put 1 resistor there. How big? I'm going to do this straight on my calculator. 1 divided by 10 plus 1 divided by 15 equals reciprocal. This is the same as a single resistor. How big? And this is my rough sketch. I'm actually just going to put a 6 ohms there. I'm not even putting a resistor symbol there. I'm saying that is replacing a group of resistors. It's not my total resistance. This is my shorthand. Then, these 2 resistors are in parallel with each other. I can replace those 2 with 1 resistor, not 25. That would be if they were in series. It's going to be 1 divided by 20 plus 1 divided by 5 equals reciprocal. Apparently, a 20 ohm and a 5 ohm in parallel are the same as a single solitary 4 ohm. These 2 resistors are in parallel with each other. I can replace them with 1. It's going to be 1 divided by 12 plus 1 divided by 12, which is going to be 2 over 12. I think when I hit reciprocal, I'm going to get 6. You okay with me so far, Spence?
Yeah.
Now, this sketch, do you notice how those 3, the 6, the 4, and the 6, are in series?
Yes.
Which means now I can replace that by adding. What if a big mess on the top with 1 resistor? How big?
16.
This is the same as a single solitary 16 ohm resistor. I tend to stick the numbers in to show that I've done a replacement rather than draw a full resistor symbol. This is my shorthand so that later on when I'm looking at my notes, I don't get mixed up about which circuit was which and where they came from. you do whatever you want. If you want to actually draw the resistory symbols like I did here, you can. It's just kind of evolved over a while. If I glanced at this, I would know, oh, that's a mathematically equivalent circuit to something over here or up here. Oh, how many amps are flowing through this?
5.
How many volts are flowing through that single ski hill? What do we, first of all, what equation are we using? I times R, right? So it's going to be 16 times 5 is what? Okay. Spencer, how many volts do we lose going through this mathematically equivalent resistor?
80.
How many volts high must the chairlift be?
80.
We just discovered the battery. We've just discovered the battery. Yes?
Yeah.
Ooh, let's go to my middle drawing here. 80, you said?
Mm-hmm.
How many amps are going through this 6 ohm? Vikas? 5. How many volts is this 6 ohm losing? How many volts are we losing going through here? I times R? Yes? 30? Right? Ready? How many volts do I lose here? 30. How many volts do I lose here? 30. Because each of those hills must be the same height as their mathematically equivalent. Spencer, do I know 2 things?
Mm-hmm.
I know 3 things. How many amps from this 5, now I can tell you how it's split up. How many amps went through this top one? V divided by R, 30 divided by 10.
3.
How many amps went through the bottom one?
3.
No.
Oh, no, sorry. So,
2. 2. How many amps are coming in?
5.
How many went this way?
3.
How many went this way?
2.
Also, V divided by R also gives you 2, this, which confirms that my mathematically equivalent drawing must be right. They rejoin for 5. Let's analyze this section by analyzing this section, okay? Ready, Spence?
Yeah.
How many amps are leaving right here?
80.
How many amps are leaving right here?
5.
How many amps are going through here?
5.
How many amps are right here?
5.
How many amps are right here?
5.
How many volts do we lose going down this hill?
20.
So each of these we lose 20 volts because that's the mathematically equivalent hill. Yes?
Yes.
Yes? With me? Oh. 20 volts, 20 ohms. How many amps?
1.
20 volts, 5 ohms. Or you could have just gone 5, take away 1, 4, but it also works by divide, right? And I love the fact that we have a built-in check. I get the same answer 2 ways. I got a built-in check. I can use either method. And then I did use the fact that these split up, but you can also see, we could now say how many amps, how many volts high?
80.
How many lose here?
30.
How many lose here?
20.
How many must I lose going through here?
30.
So you could say 30 volts, 30 volts. 30 divided by 12 is 2.5. You could say the resistors are identical. It's going to split the current, 2.5. You could say, hey, I know there's 5 amps going through there, so even though we got the 30 volts by subtracting from the chairlift, I could also have gone 5 times 6 and got the 30 volts as well. We now have multiple approaches that are giving us the same answer. Woo! This is going to be our strategy. Look for total current. If not, look for 2 things. If not, rewrite it. Ski. If not, rewrite it as its mathematical equivalent. And then ski. Okay. This circuit here would be B plus A level, but this is going to be totally fair game. There's going to be one this tough on the written section of your test. But don't worry, we're going to practice these. I think I said to somebody the other day, I love solving circuits. I almost find these like little addictive Sudoku puzzles. Like, I have to be honest, you give me 10 or 15 of these, I just love filling in the blanks and solving these. Because I get to go skiing. I'm shushing down the slopes. Ah! Here we go. Example 8, the one we just did, illustrates an important point. It shows us that the voltage drop across parallel resistors, 30 volts, 30 volts, 20 volts, 20 volts, 30 volts, 30 volts, if you have two resistors in parallel, is the same as the drop across the mathematical equivalent. There's my small version. I think it was Kiowa who was... Were you asking me about break? No, someone here was asking me about breakers. You know what? I think it was Josh who was away today. Well, Josh picked a bad day to be away. So in a standard household circuit, plugs and lights are wired in parallel to 120 volts. There's our voltage source. Now it's alternating current, but we can still use Kirchhoff's laws. It's just downhill changes back and forth, but that's okay. Each circuit has a circuit breaker in the circuit. The circuit breaker is an automatic switch, and it's designed to flip open when the circuit exceeds a set value of current, usually 15 amps. And when the switch is open, for safety, no more current will flow. The circuit is broken. If we connect a 1200 watt hairdryer and a 500 watt TV to the same circuit, will we cause the 15 amp breaker to trip? You know what? Let's draw the equivalent circuit diagram. We have a voltage source, 120 volts AC. The symbol for alternating current, so direct current is that. Alternating source, it's drawn as a circle and then with a little sine wave to show that the current is going back and forth. In fact, really, I should have that there. And then it looks like we have one resistor here, and we have one resistor here. If you're redrawing one of these, I encourage you, don't make them small. Give yourself room to write. If you're drawing the mathematically equivalent circuit, don't be scared to make it big. What have they told me? They've told me in this circuit here, I have 1200 watts. In this circuit here, I have 500 watts. Let's find total current. And if total current is bigger than 15 amps, you can't run this. Let's find out. Did they tell me total current? No, that's what we're trying to find. Did they tell me current anywhere? Is there anywhere where they told me two things? Let's ski. Ready, Vikas? How high?
120 volts.
Does this ski run here get us back to the bottom?
Yes.
How many volts must I lose through the 120 watt hairdryer? Sorry, how many volts must I lose for the 1,200 watt hairdryer?
120.
Okay. 100 and... Hey, knock knock. I know two things, I know four things. Let's see, now we're using power. I seem to recall power equals V times I and V equals I times R. You know what? I know power, I know voltage. Hey, I can tell you the current running through there. In fact, I can do it in my head. 1200 divided by 120, 10 amps, yes? Is this a legitimate ski run? Yep. How many volts do I lose going through the TV? 120. So, come here. 120 volts. How many amps? 4 even?
4.166.
How about 4.2? Okay. So here's the question. What's the total current flowing through this circuit? Are we going to trip the breaker? We're close. In fact, something this close, you may actually end up tripping it after a time delay, because as the wires heat up, that actually does increase their resistance, and that would technically, in our magic physics world, this doesn't happen, but in real life, it would add another built-in resistor, and it might cause the current to go up a tiny bit more. This is why sometimes the breaker doesn't blow right away, it blows after a few minutes. Yeah, it took a while for the wires to heat up enough for their resistance to increase, to add more current, to require more current. But in our magic physics world, Kiowa, our wires are never going to have any resistance, so we would say barely. Plug anything else in, you're almost certainly going to trip a breaker. This is also why, depending on your how your house is wired, the place that I live in, there's one plug. It must be wired to this plug upstairs, and the people upstairs must have something pretty heavy-duty plugged into it, because it's the best place for me to plug in my microwave. I can't plug my microwave into there. I'll blow the breaker every time. And I'm nice. I plug my microwave in somewhere else and rearrange my kitchen. Good enough. But there's got to be something else on that circuit upstairs. Don't know what. Homework. Mr. Derek, that was a short lesson. We're going to practice this. Number 1. Number 2. 3 is good. 4 is just asking which ones are in series. You can just label them. Remind me for number 4. I can go over the answers next class. I've just noticed there is no answers. Oops. I'm not going to make you complete the equations, though. 6 is good, so skip 5. 6 is good. 8 is good. 10 is good. 11. One thing that's nice about parallel resistors, and it's counterintuitive, so number 14 says, if you add another resistor in parallel, what happens to total resistance? Turns out in parallel, if you add another resistor, you lower total resistance even though you've added a resistor. Prove it if you can. I'll show you a couple of proofs next class. Okay?